Hello, this is Jennifer Martinez, and in this video we're going to be talking about the inverse of a matrix, denoted a raised to the negative 1, and we're going to use this to replace division of matrices. What is an inverse? Well, in algebra, for instance, an additive inverse, say like the additive inverse of 4 is negative 4. So when you add them together, you get the identity 0. We have inverses of multiplication too. They're usually reciprocals. Note, the inverse of x is 1 over x as long as x is not 0. And when you multiply them together, you do get the identity, which is 1. So with matrices, an n by n, it needs to be an n by n matrix, a square matrix, is said to be invertible if there exists an n by n matrix C, such that when you multiply them together both ways, because they're not commutative, is equal to I. And they denote that C to be A inverse, so you could write it as A times A inverse, just like we did up here. Theorem 4 gives a formula for a 2 by 2. If A is equal to this 2 by 2 here, then A inverse is going to be 1 over the AD minus the BC times this matrix D negative B negative CA. Notice how they switch the A and the D, and then the B and the C are negatives. This is only invertible, by the way, if AD minus BC is not 0. Makes sense? Otherwise, it's not invertible. From chapter 3, we're going to see that this AD minus BC is the determinant of a 2 by 2 matrix. And sometimes they donate it with these absolute value signs. So let's go ahead and show this or prove this. We know it's the inverse if we multiply it together, and it's I. So let's go ahead and do that. So here it is. This is just a constant, so I can put it on the left side. And if we just start multiplying this, we have a 2 by 2 with a 2 by 2, so the result is going to be a 2 by 2. And we're going to see the first row in the first column is going to be AD minus BC. And the first row second column is going to be negative AB plus AB, which is 0. The same as the second row first column, that will be CD with a minus CD, so that would be 0 again. And then finally, the second row second column would be a negative CB plus AD. And you can see when you multiply that together, you will get the identity. So on your own, you guys could check the other side. So to see an example of this, what I'm going to first do is look at AD minus BC. That gives me 18 minus 20, which is negative 2. So I'm just going to write down that formula. So the answer is going to be negative 1/2. And the D and the A, notice we just switch. So this would be the 6. There it is, and that's the 3. And then these ones we just put a negative, but we do not change them. So that would be a negative 4 and a negative 5. So you should get negative 3, 2, 5/2, and negative 3/2. You can multiply those and check to see if it indeed is the inverse both ways. The next theorem, Theorem 5, allows us to have another way of solving matrix equations. So if A is invertible, n by n matrix, only if it's invertible, then for each B in Rn, the equation AX equals B has the unique solution X A inverse B. So let's go ahead and show that. So I'm going to let A be an invertible n by n matrix, and B is an Rn. So the equation AX equals B can be written as A inverse. So I'm just taking the inverse on the left and the inverse on the right. And we know that it's invertible, so we know that A inverse times A, because I could rewrite this as I. So we have, there it is, it exists. The book, if you look at the proof of the book, they show that it exists, they plugged it in, and they showed it's unique. So you can show that it's unique by picking another U and getting that same result. So there it is. Example 4 shows this for a 2 by 2, but to be honest, this could be any n by n matrix once we find how to find the inverse of a larger matrix, which ironically we're going to use this theorem. So let's go ahead and do this way. So we know what A inverse is here, because A is equal to 3, 4, 5, 6. Whoops. And therefore A inverse, we did this in example 2. What was it? Negative 3, 2, 5 halves, and negative 3 halves. Let's go and check that. Yep, that's what it was. So now we can find out what X is. X is just equal to A inverse times that B, where B is the vector 3, 7. So let's try that. So here's A inverse times B. I just multiply them together. This is a 2 by 1. This is a, nope, it's not. It's a 2 by 2, sorry. And this is a 2 by 1. So we're going to get a 2 by 1. And what is that going to be? Negative 9 plus 14 is 5. And then for this one, it's going to be the second row, first column, 15 over 2 minus 21 over 2, which is negative 6 over 2, so negative 3. That should work. Let's try it. If you plug in a 5 here and a negative 3 there, that would be 15 minus 12. If you plug in a 5 here, 25 minus 18 is indeed 7. That is the solution. The next goal is to try to find inverses for larger matrices other than just 2 by 2s. And I'm going to use what I did here. I'm going to use this theorem. You notice this theorem was not just for a 2 by 2. So let's look at this example. Let's find A inverse where A is this 2 by 2. Yes, I realize it's a 2 by 2, but we're going to do this now in a different way. So our goal is to find a matrix C such that AC equals CA, which equals RI. That's our definition. And what I'm going to do is I'm going to do it in parts. I'm just going to solve, as I did the last example, AX equals E1, where we know what E1 is 1, 0. And the first part, the first column of that I, I'm going to call it X1. And what does this mean? I'm going to go ahead and solve this, not using matrices, how we normally did before. And I'm just going to get A0 there by multiplying the first row by 2. So that would be negative 6, negative 2 plus 2, or 2 plus negative 2 is 0. Negative 6 plus 4 is negative 2. And then 2 plus 0 is 2. Okay, just dividing through by negative 2 gives a 1 there, but I'm going to go all the way and get that reduced echelon form by multiplying the second matrix by 3 and adding it to the first. This first one doesn't change, but this does become a 0. This becomes negative 3 plus 1 is negative 2. So we know that x1 is equal to -2, -1. But also, from here, we can multiply both sides by A inverse, or by that last theorem. We know that x1 is also A inverse times E1. Let's do the same thing for AX2. We'll call it x2 equals E2. So what do we have? The same as above, except for now it's 0, 1. And when we do the same steps, everything's going to be the same as here. It's just the only thing that's going to be different is this last column. When you multiply your matrix by 2, for instance, this will now be a 1. And then when you divide through by -2, it would be a -1/2. And then you add 3 to the second, add it to the first, you're going to get this answer. So what does that mean? That means x2 is equal to -3/2, -1/2. But the same thing, we also know from our theorem that this is A inverse E2. So if we put this together, we've just found A inverse. This will be the first column and this will be the second. To see that, right, the idea is going to be here. We're doing I2. If we look at A/I, which by the way is A, E1, E2. So I'm now having, instead of that's where my line is, I'm having a matrix over here on the right side instead of just one vector. And we're going to have an algorithm, here it is down here, that says that if you change this to an I, we'll call it I2 in our case, then what you're going to have is an x1, right? We found that column to be x1, and the next one was x2. But we know that this is equal to, we just saw it, A inverse E1, and then x2 was A inverse E2. So this right here we just know is really just A inverse, isn't it? That would be the first column of A inverse. That would be the second column of A inverse. So it would give us the whole thing. So we would have AI2 is equal to I2 I inverse, which is what all algorithm says to do. So if you have row reduced for any algorithm and you start with A, I usually put a slash here, but you don't need to. And A is row equivalent to I, then AI is row equivalent to IA inverse. So this allows you to do this now for any size. So if you want to show this in general, I'm going to just let A be an n by n invertible matrix. And we're just going to apply theorem 5 to each column of our identity matrix, do it in parts. So solving for x1, solving for x2, and so forth. And then we're going to look at A/I. We can call it IN if you want. So IN is just E1, E2, and EN. Then we're going to row reduce it, get that to be an IN. So then this would just be an x1, x2, xn. When we did our work above, we actually got our I. That's what we did. If we just did it for E1, we just did it for E2, and so forth. And then we know that is actually equal to, we just rewrote it down here, x1 we know is equal to A inverse E1, A inverse E2 is what x2 is, and finally A inverse En. And we know, therefore, this is the first column of the inverse, second column, and so forth. So the whole thing together is the inverse. And that proves let me make it smaller, that theorem.